started with this new session, Bring the Stars Within Our Reach, presented by Ryan and Mark. Mark is remote dialing in. Thank you.
Thanks very much. I seem to have just lost my computer once again. So after all of your patience, I'm afraid I'm still experiencing some technical difficulties. Well, Mark, can you hear me?
I can.
All right. Well, thanks very much. Unfortunately, I'm now having my computer is once again rebooting. We'll go ahead and try to reboot this, and maybe Mark will skip running what was actually the point of the session, which was to show the shared control over this software that we use in our planetariums, respectively, in San Francisco and Chicago. I'm going to let my computer do its thing. The presentation that's up on the screen is actually one that is running off the computer in the back. So I'll try to do that introduction. Mark has some portions of the presentation as well. And then if luck prevails, we'll be able to get this up and running a little bit toward the end of the session. My apologies for the delays, and sorry that the wonderful technology demo may not be as wonderful as we'd hoped. The point of this session was really to showcase modern planetariums. And I personally am coming from the California Academy of Sciences in San Francisco. And that is an institution that, if you might know another famous California science institution, the Exploratorium, that's on the waterfront near downtown. We're not. The other great science institution in San Francisco is in Golden Gate Park. We're a natural history museum, aquarium, and planetarium. And as you might guess from the title of this talk, my intention is to tell you a little bit about the planetarium. So if you were to dive under the living roof of the California Academy of Sciences, one of the characteristic mountains, hills on the living roof is basically the ceiling of the planetarium. It's a 75-foot diameter dome. And if you're familiar with planetariums of maybe a few decades ago, then you'll notice that there's something sort of missing in this image, and that is the star projector, that wonderful mechanical device that once graced the inside of basically every planetarium. This is actually the Morrison Planetarium star projector that was built in 1952. It was built at a time when there was no access to high quality star projectors. They were in the United States because they were built in what was at that point East Germany. And so with typical, and since we heard this morning about some great California pride, I can say that the original Morrison Planetarium projector was the first significant home-built projector in the United States, and opening in 1952 to great acclaim in San Francisco, previously, including the original planetarium in the Western Hemisphere, Adler Planetarium, where Mark is calling in from. Those projectors were also supplied by the Zeiss Corporation in Germany. This is the first sort of significant American projector. Now, I would argue that this is actually data visualization. These are the two of the astronomers who worked on getting data into that initial system. It projected about 3,000 stars, and those star locations and brightnesses were accurately depicted with the technology of the time. And this is basically data visualization circa 1952, the locations of all of those thousands of stars printed out before being basically placed on the plates in the optomechanical star projector. But the modern planetarium is driven by technology that would be more familiar to those of us in the room. And these immersive theaters are now not just a visualization environment for the night sky, but really the three-dimensional nature of the cosmos. And that was the intent today, to tell you a little bit about what we're doing, but also to demonstrate some of the software that we use to basically not just show you the night sky, but to take you out into the universe. I'm still going to try to get that up and running. Mark is going to be able to fill us in on some other aspects of the way the planetarium community is leveraging these kinds of software platforms. I'll just note that in addition to astronomical visualization, we do a lot of visualization of Earth systems as well. We won't really talk about that today. And also at the Academy, we produce a lot of sort of finely rendered programs that are much more in the style of sort of a Industrial Light and Magic or Pixar, whereas this real-time software, which can theoretically run on a laptop, just not mine at the moment. This software allows us to do a broad range of activities, especially focused on astronomy visualization. So maybe I can turn things over to you, Mark, while I try to sort out my technology issues here at the hotel.
Sure. Thanks, Ryan. So, as Ryan mentioned, the Adler Planetarium was the first planetarium in the atmosphere. In 1930, it was founded. The first planetarium dates to 1923. So we're coming up on that centennial of the planetarium, and it's an interesting time to think about what that next 100 years will look like. So I think you've got a photo of me there in the main theater at the Adler. We actually have two dome theaters. There I am looking at some images from the Hubble Space Telescope. What we're looking at, what we're running in there is a piece of software called Worldwide Telescope. It was originally developed as a sort of an experiment from Microsoft Research in storytelling in data-rich environments. But that has evolved to something that the entire community is using. It's now supported as an open source project by the American Astronomical Society. We're now looking at actually taking this visualization software that we've been using in the planetarium for the last decade or so and integrating it into scientific papers. What it does is it gives you a portal to all of the world's astronomical information. When you're operating the planetarium in the back, you're like a VJ, you're spinning different astronomical images from different telescopes, all of which are hosted on cloud-based resources that you can access. And then if we go to the next slide, we go back, and much like Ryan did, I want to give you a little before and after image of the Adler Planetarium. So you see that original Zeiss projector, and you see what were seats that were very uncomfortable for people looking straight up in the dome. But the kind of communication we do now, I like to think of it as data visualization driven storytelling. And really what we have is this portal where we can create whatever we want. We're not limited to just starting the night sky, but we can show all kinds of images. We can customize images for the speaker. But in particular, what we were hoping to demonstrate today was a new technology, one that enables global collaboration, and that's something called domecasting. Through domecasting, we can synchronize the views in multiple planetariums, and we can transfer control of that view back and forth. We've been doing that for a number of years. The sort of main program we do it through is a lecture series that we call the Kavli lecture series. It features like very high-end scientists, some of the best science communicators, and we create for them a full program of custom immersive graphics. It turns out this is actually a lot of work, and it doesn't really make sense to do that kind of effort for a single audience. But the simulcast technology allows us to reach a global audience. So, for example, in our last one, we reached 25 different planetariums, places in Africa, in South America, in Asia, in Europe, all around the world. We actually have to do it a couple of times to account for the different time zones. And in addition to simulcasting planetaria, we can, at the same time, put out a 360-degree video stream. And so I have a slide up at the end that shows a girl in the Chicago Children's Hospital. She wasn't able to come to the planetarium to see this presentation, but here she's watching through Google Cardboard. She's able to watch this presentation in real time, and actually through the comments functionality, even submit questions.
Well, Thanks, Mark. And some good news. I am actually almost fully rebooted with the software. So I don't know if anyone has any questions about what you've heard so far, but I think we will be able to get to the demo here in just a moment. And because this is a technology-oriented conference, you're going to get all the behind-the-scenes conversation while Mark and I try to set this up to do what was nicely set up in the back of the room before I came to the front of the auditorium where you could all stare at me. So I don't know, are there any questions to get the ball rolling? And then within about 2 or 3 minutes here, I can start the 3D software. I guess I can, since I'm not seeing any excited hands being raised, I will say that what you're going to see here is a real-time application that is software that runs on, theoretically, again, this laptop, as well as a computer in Chicago, which is where Mark is set up. It also runs in both our planetariums, Adler Planetarium and the Morrison Planetarium at the California Academy of Sciences. And what we're doing in order to domecast is we're not actually pushing the high resolution images across our network connection. So basically, I don't know, Mark, what is the resolution of your large digital dome theater?
Well, it's an 8K theater, so 8,000 pixels across.
And so the Morrison Planetarium is probably more like 6,500 pixels across. So do the math, and you end up with a fairly high resolution imagery, a little bit more than even what a 4K television signal would be streaming. And so we, instead of trying to push those pixels across the network, what we instead try to do is share the data sets that we'll be using for any given presentation. And so the relatively lightweight data sets like locations of stars relatively close to home, as well as the like, for example, locations of planets and such. So so I'm sorry, actually, Mark, are you connected to the session on domecasting?
I don't see it yet.
So I restarted the CENIC 2019 Connect session. And so basically what we're doing is Mark and I have the same software loaded on our 2 machines and the same data sets. And one of the programs that we do, in addition to the lecture series that Mark hosts, and we actually have a similar lecture series, although we don't broadcast it, sadly, to kids in hospitals or to other planetariums. The 2 planetariums, Adler and Morrison, actually will do shared presentations. And so something actually that if you are in San Francisco this Thursday, if you come to the Academy at 6:30, you'll see a presentation that Mark and I will do, I hope with much greater technical success, where we're actually presenting what we call Universe Update. And it's a presentation where we start at Earth, make our way out to the cosmic microwave background, and then tell some interesting science stories along the way.
I'm still not seeing it, Ryan.
Okay.
But you could maybe just fly and they wouldn't know any better. Oh, wait.
Yeah, unfortunately, I sort of don't have anything up on my screen at the moment. I have this nice, I mean, the universe is quite dark, but this is even darker than I'm expecting it to be. So let me just see if we can. Oh, here we go. All right. Well, so magically we have appeared here at the International Space Station. And given the limited time we have left, I don't know, Mark, if you do see the domecast, I am connected. But if that doesn't work out, then I will just consider myself lucky that we actually have an image on the screen that is not black. So as you can see, I'm actually started at the International Space Station. I apologize. I normally give a little bit more of an introduction to that and a little bit more of the sense of scale that we're experiencing here because we have a human scale that we're starting with at the International Space Station. And that sort of trajectory that you see that just disappeared off of the screen is the orbit of the International Space Station around Earth. And what we have here are nested three-dimensional data sets. Again, these are locally stored in individual machines, so that connection for domecasting is really about sharing the position location as well as information about what data are being displayed and so on. So what we've done now is we've pulled back far enough to see the solar system, the sun, and the orbits of the 8 planets. And assuming everyone here is old enough that you learned there were 9, there aren't, there are 8. Pluto doesn't care, you shouldn't either. But the nested data sets here are kind of, they come with sort of a set that you can expand on. And so something that Mark at the Adler and we at the Academy of Sciences do quite a bit is extend this collection of data to tell news stories about breaking news. And so like one of those, I'll just say, I'm added an orbit here that's not a planet. This additional trajectory here is the orbit of the asteroid Ryugu. Does anyone happen to know what spacecraft is visiting Ryugu? It's not a NASA mission. And even the NASA mission to the asteroid OSIRIS-REx hasn't gotten as much press as I would like. But this is an asteroid being visited by the Hayabusa 2 spacecraft. And it's actually landed a couple probes on the surface. We'll continue to do that. I think it's a total of 5 probes it's landing, and it's 2 of them have landed. But in the process of going into orbit around the asteroid, the Japan Space JAXA, the Japan Space Association, released this 3-dimensional model. We were able to import that into the software. The one thing that's probably the most distracting is that Ryugu is nowhere near this bright. The reflectivity of these asteroids is something more like the reflectivity of coal. So here, in order to visualize this and give you a sense of what the spacecraft is visiting, we imported this 3D model but gave it a little bit brighter coloration to give you a sense of what the spacecraft is exploring. Now, Mark, can you actually see what I'm doing, or are you?
No, I can't.
Okay. Well, how about if you were to blindly describe the data that you so kindly supplied us for this presentation. I'm going to go ahead and go to the asteroid data set that you provided,
Sure.
which is, I think, a great example. We're flying there now. And so now that we've actually visited a real asteroid, I'm going to take you to a simulation of an asteroid. And Mark can take it from here. We're just approaching the asteroid now, and we'll kind of pop on it in its multicolored glory here in a moment.
So one of the things we try to do in this Universe Update program is really focus on really current science. So last Sunday, there was an article in the New York Times that said something like, if you blow up an asteroid, it just pull itself back together again. And that seemed kind of fun. After reading it, sent an email. Well, first I found the lead researcher, Googled him, got his email, sent him an email, asked for his data. He sent, on Monday, he sent us about 20 gigabytes of simulation data. And then the next couple of days, put that together with your see. So you want to explode that asteroid?
I will explode the asteroid.
And so the idea is if we have an asteroid headed towards Earth, we don't want to wind up like the dinosaurs. And one idea has always been that, well, we could just go Bruce Willis on it and blow the thing up with some nukes. The problem is that gravity tends to pull these things back together. So that visualization you just saw is actually only occurring over 3 hours of time. This asteroid breaks apart into many, many pieces, and it will pull itself together. So
I can rerun
we
the
have to
simulation.
think about better strategies for dealing with it.
I'll rerun the simulation. We're a little greater distance here, so you can kind of see what's going on. And so yeah, you can observe there that basically what we're modeling is an impact of a smaller asteroid on this larger impact of the larger asteroid when that impact takes place on kind of the bright, lighter side of the way the data are being depicted here. That impact scatters a lot of stuff off, but you'll notice that over time, as Mark said, a simulation time of about 3 hours. A lot of that is falling back onto the surface of the asteroid. So that's actually one of the stories that we plan to tell this Thursday. Again, that's kind of breaking news. The story, as Mark noted, appeared just a little over a week ago, and because astronomers are friendly sort and typically willing to share their data, we were able to get the data ingested into the software quite quickly. So thanks to the Adler team for doing that. I'll just go ahead, and I think we have just enough time to be able to. By the way, I'm kind of spinning everything quite quickly here, which we don't do in the dome. The immersive space of the planetarium theater or even of a VR headset is really such that you don't want to be moving the camera, the virtual camera, as quickly as I have been here, because instead of just viewing this sort of rectilinear image at the front of a room, you're immersed in it in a planetarium like Adler or Morrison. But I already mentioned the 8 planets. Let me go ahead and get rid of Ryugu there, our charming little asteroid. But actually, there is, of course, the former planet, Pluto. And as you may know, it was visited a few years ago by the New Horizons spacecraft. I'm actually showing the trajectory of not just New Horizons, which is this one here, but also the trajectory of our fastest spacecraft. These are the fastest sort of nuts and bolts objects that we've sent out into space. But you may know that at the beginning of this year, in addition to visiting, I'll just go ahead and add Pluto to this image here. So that's the orbit of Pluto. And you can kind of see that bright orbit. That is was encountered by the New Horizons spacecraft back in 2015. But New Horizons went on to explore the sort of dramatically named 2014 MU-69, which, because the name didn't quite excite much interest on the part of the people who were writing press releases, they chose to kind of rename it Ultima Thule, which is a reference to sort of the last place on the map and potentially the outermost object that would be explored by a spacecraft sort of in situ. Now, as we come up on Ultima Thule, kind of like the model I showed you of Ryugu, this is a three-dimensional model of the asteroid. And when we first saw this asteroid, we saw it kind of, I should say Kuiper Belt object. It's in the outer reaches of the solar system. It sort of presented itself as what we imagined as sort of two spheres just barely touching. And you can imagine an asteroid impact that's not as dramatic as the one that we saw simulated that Mark was showing, that's more of a grazing or touching impact, could cause two objects to sort of fuse together. And initially we thought these were two spheres fused together, but as the New Horizons spacecraft zipped by Ultima Thule, and by the way, in real space, this is, again, darker than we're showing it here. It's brighter than the asteroid there because it's an icier object. But like when we were on the other side, it looked like it was kind of backlit. There's no backlighting in space. So in fact, what the spacecraft had to do is look back at the sort of shadowed figure of this asteroid, and it determined that the asteroid is, or this Kuiper Belt object is not two spheres connected together, but rather the larger part, called by the planetary scientists Ultima, is the sort of flattened pancake shape, and the smaller part, called Thule, is sort of more like a walnut kind of shape. Now, this is not the exact shape, and sadly, there's actually a press conference today, and I was hoping to incorporate some new information from that press conference about this. There's a gathering of planetary scientists taking place right now in Houston, and they had a press conference about this today. Unfortunately, I was busy addressing technical issues, all the good that did me too, to figure out what was going on at the press conference. But again, this is kind of a platform for us to be able to talk more about recent discoveries in astronomy. And I guess basically just for kicks, and I apologize, Mark, because I'm just going to kind of put the pedal to the metal and try to give people the experience that is the context for this overall planetarium show that we do once a month, this universe update. I'm actually leaving the sun behind here. We're now seeing the individual stars, the sun retuned to be about the same brightness. It doesn't show up terribly well here, but we're traveling through an accurate three-dimensional data set of about the most 100,000 brightest stars in our night sky. We can also highlight the locations of exoplanets, so planetary systems other than our own solar system. This is an artist's rendering of the Milky Way galaxy, the hundreds of billions of stars in which we reside. And we're actually seeing these sort of points of light fading up. These are the locations of not now individual stars, but galaxies. So each point represents the collections of hundreds of billions, if not even in some of them a trillion stars. Rather faint here on the monitor, but as we pull far enough back, you can see more of these points that represent the very distant reaches of the Sloan Digital Sky Survey, a high-resolution imaging of the sky that allows us to determine the accurate distances to these galaxies and quasars, which are even farther out from our Milky Way. And I've pulled far enough back here to see what we call the cosmic microwave background. So this is a little bit faster than we present it in the planetarium. But this is sort of residual light from the Big Bang. And as one of our colleagues has described, what we've just flown through very rapidly from the planets and other objects in our solar system out to the nearby stars, out to our galaxy, the collection of galaxies near to home, the galaxies much, much farther away that show a distribution you can't see too well on the monitors, but a distribution that's limited by our observation from within our own Milky Way galaxy, on out to this observation of the oldest light in the universe. He refers to this as sort of a Christmas tree, and you can put the decorations on the tree to flesh out the more contemporary science stories and the more cutting-edge stuff. But this is a scaffold on which we can use to present cutting-edge data. And as Mark noted, what's really powerful about this is that when it works, it can really run well on a laptop. So you can imagine this laptop in a school or on the road. One of our colleagues goes out to Thailand and Cambodia and presents with this. And with a relatively narrow pipe, you can communicate across great distances, share a virtual space, whether it's between Chicago and here in La Jolla, or whether it's in within a state at different schools, or whether it's at planetarium domes across the world. And that potential to sort of share virtual space, to hand off control, to really share this virtual environment, which here we're using to illustrate astronomical concepts, but really is a flexible visualization environment that can be used to as a shared space to explore many different kinds of science topics. This is a really interesting potential that we've only begun to tap into. So it's something that I'd be delighted to have conversations with people about throughout the rest of the day. Unfortunately, I'm only here for the rest of the day. But because I don't like to just leave people hanging out billions of light years from home, let's go ahead and I need to do one small adjustment here. I do at least want to take you home. So this is, again, that limited view of the universe around us that we have from the Sloan Digital Sky Survey, passing through the tens of thousands of galaxies close to home that we can't see terribly well on the monitor, into the spiral disk of our own Milky Way galaxy, back into the collection of about 100,000 stars that are relatively close to home with well-determined distances, and back to our own solar system. Our star, the sun, appearing just as one star among many initially. And as we approach it, we fade it down so we can see the orbits of those fastest spacecraft that we sent out into space, the orbit of Pluto, the non-planet, as well as the 8 planets in our solar system. And finally approaching Earth, our own third rock from the sun, so it can at least return us to where we started. So with that, you kind of got a demo of the software. I'm happy to talk more, and I'm certainly happy to answer any questions, and I think Mark can stay on the line as well. So thanks very much. And I should give a big shout out. All hardware, software problems were my own. Brandon and the tech team here was very helpful in setting stuff up so that I could at least try to fail in front of all of you. So I appreciate their support in getting us network connectivity and a Skype call and all kinds of crazy things so that we could at least give this a shot. So I don't know if there are any questions. I think we have a couple microphones. And
hold it in. There it goes. You mentioned that you were thinking it might have other visualization aspects beyond the planetarium. What, did you have any other examples that you were thinking about?
Well, so I should note, actually, so the software that we were running here is software that it's commercial software, and there actually is now emerging open source software that can do the same kind of domecasting kind of stuff. And everyone who's building these kind of software platforms now, I mean, astronomy, as it turns out, is easy. I mean, space is basically a vacuum. You put some points of light representing stars, and you've got something that's interesting to look at that's relatively scientifically accurate. Now, the way these are structured, because you need to be able to go from the cosmic microwave background down to the scale of the Earth or the scale of the International Space Station, that's larger than a larger range of scales than computers have built to handle. So you have to deal with nesting smaller and smaller scales. So in theory, there's no reason why you couldn't go down to the atomic scale with this in terms of the structure that's been built. So then the question is, what exactly are the tools you need to visualize things like molecular processes? We don't really have that kind of stuff built into the software. So we can show like a kind of hard body model of a molecule and give you a context in which that might exist. But the kinds of storytelling that we really could start to explore, we haven't quite got the tools for. So the tools that we currently have are good for kind of hard bodies moving around in space, and they're good at layering data on Earth. So a lot of the stories that we tell at the Academy of Sciences are stories that our researchers are involved with. So KML data overlaid on Earth, showing where our researchers are doing work. We can fly people down to their locations, put it in context. So if you want to talk about reefs off of the Philippines, where we do a lot of work at the Academy, we can layer in data that allow researchers to talk about that. But it's data that gives a kind of regional or local context to their discoveries, rather than sort of taking you down to the scale of the coral polyp. To do that, we'd go back to the kind of more Hollywood toolkit that I mentioned before to do visualization that's not real time. So I think the potential is quite broad, but not all of the tools have really fallen in place. I don't know if that quite answers your question. I mean, part of the problem too is if you build a hammer and you only give it to carpenters, they're only going to think about pounding nails. So this tool technology is really in the hands of astronomy educators right now. And so until we kind of expand the people who are using it, I don't think we'll see more of the real potential in terms of the kinds of stories that can be told. Another question on the opposite side of the room, because that's how questions happen.
Two questions. One, the girl that was in the children's hospital, was that being live broadcast to her, or was that software installed on the smartphone that was inside her 3D viewer?
So that was live stream 360. And we shipped some of the headsets beforehand to children there.
So mine have kind of dropped out, but he said live stream through YouTube 360.
And then the second question would be, you mentioned that as of right now, it's designed for hard bodies with being able to do the dome casting. How likely would that possibly be more with photography from like a physical geography perspective?
So, I mean, one of the things that we can do, and we do it for Earth and for other planets, is we can insert a panorama. Actually, I could actually, well, if I had time, I could show it to you, but we could actually like land you on the surface of Mars. So actually, as I'm answering the question, I'll try to do two things at once. But we can actually create sort of panoramas that will, particularly in a planetarium dome, are really great at sort of immersing you in an environment. So let me go ahead and take us to Mars really quickly. So it's not as continuous as what I showed you here, where we kind of elegantly-ish fly away from Earth, and so let's see here. Let me get crater centered here. So the Curiosity probe is on the surface of Mars. And so what we've done is we've kind of put, again, because the software can accommodate these varying scales, we put Curiosity to scale. It'll kind of pop on in the center of the screen here, but notice that we've reached the limit of the data that's stored locally on my laptop. We can page in higher resolution data from NASA servers. We're also coming in at a weird angle, but this is the Curiosity probe on the surface of Mars. You can see its little robotic arm doing its robotic arm stuff. And so we can kind of provide context here. And this is actually surrounded by an actual 3D terrain that's derived from Curiosity observations. So we can do something similar on Earth if we want to show a location. Like we did a great presentation on Rapa Nui, and our researcher who had gone there had taken many 360 images, so we could drop those in, and basically it's kind of like hopping from location to location. You can put those in the context of like a georeference sort of, again, kind of Google Earth KML type look, and then you can pop to different locations to sort of see what that looks like. Recreating a three-dimensional environment is a little more challenging, but we're beginning to do it for Mars. Again, Mars, trees are not amenable to the photogrammetry that's used to create these kind of 3D terrains, but rocks are. So it's a lot harder to do a 3D reconstruction of, say, the Amazon rainforest, a lot easier to do something like a 3D reconstruction of a rocky plain on the surface of Mars. So those are the kinds of things that we're working on. All right, I think I'm out of time, but thank you very much.